So our next session is session 8, Corrosion Barrier Coatings 1. It is chaired by Professor Mikhail Zheludkevich, who is currently head of the Department of Corrosion and Surface Technologies and at Helmholtz-Zentrum Geesthacht in Germany. He's also professor at the University of Kiel and invited researcher at the University of Aveiro. His research focuses on electrochemistry, multifunctional surface, and active protection of light materials and multi-material systems. Additionally, he is a member of the technical group in Research Fund for Coal and Steel and is vice chairman of the Aerospace Working Party at the European Federation of Corrosion. He was awarded with the prize of Best Young Portuguese Electrochemist, and he has published more than 140 papers, 12 book chapters, and he's co-inventor in 12 patent applications. So, Mikhail, the floor is yours, and enjoy the session.
Okay, good morning or good afternoon, depends where you now currently. Thank you for introducing me with probably too many details. And today we have our session related with corrosion barrier coatings. But indeed, if you look to the work program of talks in our session, we are not only focusing primarily on barrier coatings. Barrier coatings are considered also as a basis for functionalization of the surfaces. So we are talking here today in our session also about functional coatings and active protection coatings, because from my point of view also it is the future for many applications when several functions are combined together, corrosion protection function with other functionalities. And I'm really glad to see here today in our session a set of excellent talks. I've seen already most of the presenters today, somewhere the names. Those who didn't, I think two last presenters are not yet in the panelist list. Please then join when your time comes. But now at this moment, I'm really glad to introduce first keynote speaker is Professor Joao Tedim from University of Aveiro from Portugal. And he's going to talk also about more functional coatings and the basis for functional coatings, which are often designed using nanocontainers. And this will be the direction of talk of Joao. Joao, please, floor is yours. You can go ahead then.
Yeah, so first of all, thank you for the invitation to make this presentation. As you said, I'm going to make I will try to make a kind of general presentation on the perspectives that we have been facing on development of coatings using this approach on including micro and nano containers. Before I start, of course, I have to say that this is not a one-man's job, as everyone knows, and actually I need to acknowledge the colleagues that have been part of this journey and these works, starting by my mentors, by Mario and Mikhail, also my research fellow colleagues from University of Aveiro, from our group, and of course all the PhD and postdocs that are not with us currently, but that at some stage have been with us and participated in some of these works. I should also say that some of the data I'm going to show today are not within exactly our expertise, and they were done in collaboration with other groups. One of the group is from the computer simulation and multi-scale modeling, namely Dr. Richard Gomes and Gerard Novelle-Leroux, and also the biology group, which helped us on the environmental assessment of the nanomaterials. And of course, the slide is too small to acknowledge every partners in this journey, but also I should say that this work was done in the frame of several projects in collaboration with several colleagues, including some institutes and companies as well. So when I was preparing or trying to figure out what would be the topic of this presentation, I came to my mind some of the seminal works that actually were kind of inspiration for me, and I suppose for many working in this field. And I realized that there's been already around 2 decades since the first works that we have seen about self-healing have come out. And when we are talking, as Mikhail mentioned, about functional coatings or smart coatings or responsive coatings, we think it's relatively new, and it's probably still very new topic. But as I will try to show today, there are still some things that we as material scientists trying to develop these systems can do to improve and to help them become indeed a reality in terms of industrial products. So just to make a kind of a common ground on the understanding of the concept I'm going to talk today, one of the ideas on this concept related to micro nano containers was actually that we would try to use a corrosion inhibitor that would actually be the active species conferring active protection, and we would try to somehow immobilize or encapsulate it in a inert or hosting structure whose main function was to store and release in a controlled way these active species. And hopefully the interaction of these, or the combination of this corrosion inhibitor with the container, would provide a kind of additive for coatings that would eventually surpass, equalize, or even surpass some of the most relevant inhibitors for some applications, namely chromates, trying to have, of course, remove the environmental or the harmful effects associated with some of these species. So I think this was one of the primary ideas and concepts coming to this field, let's say. The approach, I think that at least the approach we have been following over the years, and I think most of us working in this field have been trying to do, was basically following kind of different stages of development, in which in the beginning we would try, of course, to find the active species for the application. If we are talking about corrosion protection, it's a corrosion inhibitor. If we are talking about corrosion detection, some molecule with a sensing ability, or for antifouling coatings, antifouling compounds. So there was an initial stage of selecting and screening the active species. Then we would take into account the physical chemical properties of these compounds and the targeted conditions or wanted triggering conditions, and try to immobilize these species or encapsulate them in different systems. The list is very wide among ion exchange clays, mesoporous materials, polymeric capsules. There are many systems that have been published so far to be it would be too extensive to mention them, but there are indeed several systems published by many groups around the world. And after this immobilization or encapsulation, the idea, of course, was to make some kind of validation and evaluate the materials. So in addition to the characterization of morphology, textural properties, particle size, it was also relevant to validate the release mechanism, triggering conditions, and of course then test them in model coatings and modified coatings to try to really see if there was an increase or in terms of the performance. And if you are talking about corrosion protection, we are talking also about the extent of the protection of the underlying substrate. But quite often, of course, it was also necessary to go through optimization stages, which include not only changing the surface of these materials to control or change the loading or combine different species, but also and very often in collaboration with industry, it is very necessary to modify also the formulations. The coating formulations are complex systems, and to actually get the best of the two worlds, a compromise between the barrier properties and active corrosion protection, quite often the recipe of the formulation needs to be changed and needs to be addressed. Now, looking at this approach, which I think, as I said, I hope I'm trying to be as general as possible. I find that we are currently living in a stage where looking at these stages of development as a material scientist working more on the experimental field, that there are several tools that we can try to use to even improve more the way we are trying to design and get these materials and get more information about them. And that's basically the content of the topic I will try to have now. So In terms of the screening of active species, I will show a few examples on how we can use interactive data tools, machine learning, and molecular modeling to help us selecting active species. I'm also going to talk in terms of materials design and showing some examples on how we can use DFT and classic molecular dynamics to get a better understanding on the stability and the dynamics of the release of active species. Of course, in terms of evaluation, quite often, and one of the primary goals when we were doing these materials in the very beginning, micro nano containers, was to get more eco-friendly materials compared to existing pigments and compounds, and that needs to be proven. So the environmental studies are necessary even to validate the importance of the material, and also what is the environmental impact when we are introducing this in a product. And of course, using that information, eventually try to modify the materials in a way that we reduce its environmental impact. So concerning the screening of active species, there are different possibilities. In this case, we can actually, based on existing literature, build data applications in which we can help us selecting compounds for certain conditions, as we have here this example. I'm not going to go into much detail on this data application because my colleague Tiago later today will present in this conference actually his data application. So I'm just going to present this as a possibility here. Another possibility for the screening of active species is actually using machine learning models based on different chemical descriptors, properties, and conditions, and use them to select untested candidates before even going into the lab. The example I have here is from a recent work we published in which we tried to compare different machine learning models and to consider to see which one would be the best to consider different conditions. Here, the conditions we were testing were data for 2 alloys and 2 pHs. Another possibility in terms of screening, of course, is using DFT, which has been used, I would say, widely by some groups, not only to calculate absorption energy and understand the interaction of the molecules with the hydroxides or the oxide, hydroxylated oxide, or the bare metal as a function of the pH, but also to have insights on the speciation of the inhibitor that we are talking about in terms of acid-base equilibria and tautomeric equilibrium as well. So other possibility is actually to use molecular dynamics, and we can use ab initio molecular dynamics to, in addition to the absorption energy, so to the stability of the interaction, to get some information on the dynamics of the interaction. Here I'm showing an example of a triazole isomer interacting with the surface, and we can see that in the presence of chlorides there is a competitive absorption, and we can use this sort of models for very short time frames to understand a bit of this interaction, and even realize that, for instance, in this case, this compound that was being used, this isomer of triazole, was not very efficient from the experimental data that we obtained, and we could somehow understand this lower inhibition efficiency with this competitive absorption, with the chlorides on the surface. So we can use the computational tools not only to obtain information on the stability, but also on the dynamics of interaction. Talking about materials design, of course, one of the systems we have studied for a very long time over the years were layered double hydroxides. These are ion exchange clays. And these ion exchange clays are built of positively charged mixed metal hydroxides. And between the mixed metal hydroxides, we have labile anions and water molecules which stabilize the structure. And so a long time ago, we have seen that depending on the inhibitor that intercalate there is a controlled release, and we can actually use this to render active protection to the substrates. However, in spite that we are able to characterize and see the expansion of these basal spacing, so the distance between the layers when there is an accommodation of the corrosion inhibitor. So there is a proof, a structural proof that the compound is intercalated, and then later we see by release studies that is released. That is not, it's necessary to also have additional understanding on how the inhibitor is there, and how to basically have the possibility to have the molecule organized and the water molecules there as well. So here in this example, we use the classic molecular dynamics, and you can see in this snapshot of the simulation that the MBT, the 2-mercaptobenzothiazole that was being used as the inhibitor, actually is interacting with the heteroatoms with the hydroxide sheets, while the aromatic ring is pointing towards the middle of the gallery space. In addition to these kind of interactions, we could also see that the basal spacing obtained from this modeling, from this simulation, was compatible and consistent with experimental XRD results. So these are examples of ways on how we can use the molecular dynamics to understand the position of the inhibitor within the galleries. We can also use DFT to calculate to estimate surface interaction with the material. Here we were using LDH, so layered double hydroxides, but as conversion films grown directly on aluminum alloy 2024. And we could see actually that the aluminum alloy had the plates of the LDH pointing normal to the substrate. And indeed, we found by the FT that the most favorable interactions between the LDH clusters and the surface was on the normal direction. So here we also have some sort of validation of how we could see the orientation of the plates and the whole crystallization process. Perhaps one of the most interesting things that we have associated with LDH is this controlled release, this ion exchangeability on having exchange of intercalated inhibitor with some species in the environment, most notably chlorides. We have seen in 2012, in one of the studies where we have published, that there was a controlled dependence on the nitrate release from the LDH in the presence of chlorides. More recently, we tried also to use molecular dynamics to try to see the very first beginning of this interaction. And what I'm just showing here is basically a stabilized LDH nanoplate in which we have the chlorides being exchanged on the edges of the LDH on a very short time frame. So we are talking about a nanosecond time scale, and what we are trying to do actually is trying to increase the simulation time so that we can see what happens in the later stages and try to approach more the experimental release time scale that we see. In fact, going to a more experimental approach, as I mentioned in the beginning of the presentation, it's also very important that we understand the environmental impact of the things we are trying to develop. As probably some of you know, MBT is a harmful species for the environment, although it's an effective inhibitor for aluminum alloys. And one of the things we tried to address was to see what was the effect of having MBT intercalated on LDH for the environment with respect to the known encapsulated or immobilized MBT. So in this study with the colleagues from biology department, we basically exposed the different marine species to the MBT in the free form and intercalated in LDH. And we could see that in all the cases, the toxicity of the MBT decreased when it was immobilized. And it's consistent with the fact that not all MBT is available at once to work on the surface, or and consequence not available to the environment. So this was a positive effect. So the LDH itself with nitrate did not have significant toxicity, or no or low toxicity at all. And we could see that when we were intercalated in corrosion inhibitor, actually we were decreasing the corrosion inhibition of the free compound. Another study was done with additives that we wanted to somehow use to help us detecting corrosion, coating degradation or initiation of corrosion processes. One of the systems we developed was silver nanocapsules we have here with phenolphthalein. So we were using pH indicator to reveal increase in pH on a coated substrate, and we could actually see that only the encapsulated form was actually able to turn color, whereas the free phenolphthalein could not turn color. So there was a deactivation of the phenolphthalein when it was dispersed in the coating. Another type of additive that we were also considering was developed more recently. We actually intercalated hexacyanophorate, and in this case, the idea was the intercalation of hexacyanophorate on LDH and control the release of hexacyanophorate in presence of chlorides. And we could see that indeed the released hexacyanophorate would then react with the iron cations from the anodic alpha reaction and form well-known blue pigment, Prussian blue. And we could see these not only upon polarization, anodic polarization, but we could also see when we were trying to use kind of even drops experiment where we had sodium chloride solution with the LDH pigment dispersed. As you can see here over the time, there is this yellowish color associated with the release of hexacyanophorate in presence of chlorides, and with time you see the formation of the blue precipitate in the middle associated with the reaction of the iron with hexacyanophorate. So why I'm presenting these additives here, because not only to change the coatings, but if we want to change coatings, we also have to be sure about the environmental impact that these materials can have. So our colleagues in the environmental studies were actually trying to see what would be the effect of the intercalated or immobilized and the free sensing compound. So they saw for the LDH, similar to the MBT, that the LDH was actually helping reducing the toxicity effect of the hexacyanophorate, which was not very high compared to MBT. But for phenolphthalein, we found different results. We saw that the silica phenolphthalein were actually inducing toxicity more than the free phenolphthalein. And this was ascribed to the presence of remnants of the surfactant from the synthesis. And we could not take the surfactant. We could try to use washing, but we could not calcine the silica. Otherwise, we would also calcine phenolphthalein, which is also organic compound, and we would lose the sensing ability. So to introduce our last point of the presentation, we use this information in a way to try to come back to the synthesis process and using a safe by design strategy, try to see if we could change the material that we were using. So instead of using CTAV to stabilize the emulsion in the, this is an oil in water emulsion to encapsulate, here is the process for MBT, but it's similar for phenolphthalein. We try to replace CTAV with a surfactant that we synthesize, a Gemini surfactant we synthesized in the lab, which was found to be less toxic than CTAV. So we obtained the capsules, and actually here we can see example of these silica nanocapsules obtained using another surfactant, and we were able to intercalate and immobilize this active compound, which was phenolphthalein. The question was, were we able to reduce toxicity of these capsules with a different surfactant? Yes, indeed, we were able to see that there was a reduction on the toxicity when we were comparing the silicas obtained with the CTAV surfactant with respect to the Gemini surfactant. So it's not a fully non-toxic material, as we can see, of course, but it shows a way as we can follow, so as material scientists, as we can try to follow, so to come back to the synthesis process and replace some of the most harmful compounds in order to achieve better properties. So as I was saying, the use of this QSP212 surfactant result in less toxic capsules than those prepared with CTAV. So last but not least, of course, I'd like to acknowledge all the funding, because I'm just showing here a glimpse of several works done in collaboration with different groups. And so I would like to thank the funding organizations and you all for your attention. Thank you.
Thank you, Joao, for very interesting presentation. And now we have chance for 1-2 questions. If there are any in the room. We are a bit delayed, but also the delays accumulated from the previous session. So we still have a chance to. So I don't see any questions. I can just ask one question from my side. When we're talking about smart coatings with nano-containers. You know very well also that not only the performance of capsule decides about performance of the system, but also compatibility. How do you see this issue and how you address this issue of compatibility between barrier layers? Then, because as I mentioned already, one of the functions still corrosion protection and this barrier, which is based on the barrier, and these functional elements that you introduce in the coating system.
Well, the answer is not very easy to give, because we see in several works in the literature, including ours, that on one hand, one point is to go, and in terms of proof of concept, you use a simplified model coating, almost just polymer layer in most of the cases. And of course, we are working with, let's say, compared to commercial products, simple polymer systems, so they are not final coating formulations. When we actually try to modify coating formulations, we often see, when we try to modify these optimized coating formulations, we see sometimes decrease in barrier properties. So it's very important that if we really want to have a realistic understanding, we not only have to take into account that we are including something that we hope that will improve the corrosion protection, but at the same time, we need to understand how these materials we add are affecting the coating, or the coating formulation first, like in terms of your rheological properties, for instance, or even the final coating if we have some of these particles or capsules that their relative size, aggregation, dispersion properties, and really try together, as I was saying in the beginning, the best approach I have seen, the less painful, is actually to work with coating producers when you are trying to do this sort of modifications, because you are doing this with someone that understands the full complex recipe of their formulation. And when you are trying to add something, it can be done together with them, so that they also help us somehow open the formulation to accept these new additives. And this is, I think, is very important.
Okay, thank you, Joao, then, for an excellent talk. I don't see any other questions at the moment. Please, if you have any, you can post it in question and answers, and then Joao will be able to answer in written form those. And we continue then with our session. We are going to our next talk, invited talk, which will be given by Dr. Carsten Blawert from Helmholtz-Zentrum, a colleague of mine. And he today is going to talk about also different strategy of functionalization of coatings, which have been studied quite a bit, as part of antioxidation coatings and considered for corrosion protection, but also those coatings have a great potential to bring additional functionalities. And this will be the topic of the talk of Dr. Blawert today. And Carsten, please, floor is yours.
Thank you very much, Mikhail, for the nice introduction. So today my presentation would be about multifunctional PO coatings, and I would basically focus on surfaces with photocatalytic activity on light metals. If we basically look on the possibilities and what we want to do, because the idea behind is somehow to design an easy to handle and large area photoactive surfaces for wastewater cleaning. We were actually selecting titanium dioxide coatings as the solution for it. And from that point of view, because titanium dioxide combines good chemical stability, it has good tribological properties, and as well has good photocatalytic activity. And we have to see that the titania actually exist in different polymorphs, but for us the most important ones are the anatase and the rutile phase, where we can basically see that the anatase has higher photocatalytic activity, but the rutile phase is better for tribological properties, and also the chemical stability is better. And what is quite important for the PO processing is that anatase tends to transform into rutile if the temperatures are actually higher than 600 degrees Celsius. So overall, one can say that titanium dioxide is probably the most widely used photocatalyst. And because it is really quite stable in even harsh environments. And in spite of the negative point, we have to consider here that the band gap of the titanium dioxide is relatively high. So we can only use UV light irradiation. But this we will address definitely in other research, which I will not talk about today, because you can also, by additives adding into the PO process, also try to reduce this band gap. But this is not the topic of today's presentation. So the question is actually, titanium dioxide layers are quite easily produced on titanium alloys. But the question today will be, how can we actually produce the titanium dioxide layers on other substrate, light metal substrates, which are, for example, cheaper. So in cheaper solution instead of using titanium sheets. So I will address in the beginning how we can do it for magnesium. Here I will show that the particle addition and transfer of particle properties is somehow a possible solution. And I will also address aluminium. And here, because aluminium is much more stable in PO processing, it can be operating also in acidic PO conditions. There we have also option for a direct titanium dioxide deposition. And to optimize, we can also combine it again with particle addition. So when we actually, or for those who are not so much familiar with the PO process, I would like to give a short introduction into the PO processing. And if you look basically on the system, you see that you need an electrolyte and you need an anode and a cathode. Your workpiece is the anode, and we basically apply energy, mainly in the form of current or voltage, to the component in the electrolyte, and that drives actually metal dissolution. And on the surface, a passive film grows, and this gives us a dielectric layer. And as soon as the breakdown potential of the dielectric layer is reached, and that you see nicely on the right, you can get uniform distribution of short-living discharges on the surface of your component. And that gives you high localized temperature and pressure, which is basically responsible for the formation of our ceramic oxide coatings on the surfaces of the light metals. However, those sparks are not only beneficial, they basically also damage the coating. There are remaining of the discharge channels and also inclusions, because there are melted phases available in which gases are dissolved. They are also causing this porous layer structure because of gas inclusions and the remaining of the sparks. And overall, the coating, one can say, is in most of the cases actually a composition of the alloy plus the electrolyte components which we are using. And one can use different processing conditions to actually adjust between amorphous and crystalline phases. So when we are actually looking on the microstructure of those PO coatings, you see, regardless which electrolyte you're using, whether it is phosphate or silicate, it basically is porous. And we have also studied this porosity in more details using tomography. And it basically turns out that the pore system is very complex. We have lots of pores which are interconnected to other pores. And definitely there are always pores which actually goes from the top view or from the top of the surface down to the interface. And this is basically critical for the corrosion resistance. But on the other hand, it offers also, because those pores are already present during the PO processing, the chance for in situ incorporation of particles or the infiltration of compounds and particles via post-treatments to basically functionalize the PO surfaces. So when we are coming now to the first example, how we can functionalize magnesium alloys, I would like to show you a little bit what we did. So basically you use a standard electrolyte, a phosphate-based electrolyte, and we have added here different amount of titanium dioxide particles to the electrolyte, which is basically anatase because it has the better photocatalytic properties. And we used two different voltages. So it was a constant voltage processing in the PO case at 400 and 500 volts, basically to see how the effect of different energy levels are on the incorporation of the particles. So when we look first on the surface morphology, in the upper row, you basically see that we have the 400 volts treatment, and in the lower row, we have the 500 volts treatment. And if you look in the surface morphology, you see that up to a certain limit, which is about 20 grams per liter of the anatase particle added to the electrolyte, the surface morphology looks somehow similar for all. But at 500 or at 20 grams, it basically starts to change. We see that the particles start to fill the open pores, and we see effects of sealing. So what is actually going on? You can see here nicely in the cross sections. On the left, you see line scans, and on the right side, there is the cross section of a coating produced at 20 grams per liter anatase addition and 400 volts. And what you clearly see is that with higher temperature and with increasing, with higher temperature, you basically, if you compare the 400 volts and the 500 volts at 20 grams, that you can keep more concentrated titanium dioxide particles on the surface in comparison with a higher temperature and with increasing concentration. But that I will show you in the next slide. Basically, you are increasing continuously the titanium dioxide concentration on the surface. And looking at the mapping and also on the line scan, it is quite obvious that most of the particles are incorporated via the surface. They are sticking in melt pools on the surface and are immobilized there on the surface. But however, there is titanium dioxide throughout the full layer. And this indicates also that there is chance to incorporate them via the open pores, and they can reach even the interface. So, but for the actually photocatalytic properties, it is more important that they actually stick at the surface. So what is our increasing amount of titanium dioxide additive doing is that we are continuously can increase the titanium content on our surface. And we can finally reach with a 20 grams addition, regardless whether it is running at 400 or 500 volts to process somehow up to 20% of titanium dioxide or titanium at the surface, but the titanium actually is an indication that we have titanium dioxide mainly. And this I would like to show you in the next slide. If we are looking at the phases, you can clearly see from the standard electrolyte on the top, 400 on the left and 500 volts at the right side. If we're looking first at the 400 volts, you see that with increasing amount of particles adding, we see them also in the diffraction patterns. So they are coming basically first the anatase peak, but you see also with longer or with higher energy and more amount of anatase added that also the rutile peak is coming in the diffraction patterns. And if you compare 400 and 500 volts, you see also that at the higher energy, you are stimulating also in reactive incorporation, what we normally do not really want to have, because it will destroy the photocatalytic activity of our particles, which we added when we are forming the magnesium titanate phase. But it has another effect when this phase is forming, because then you get nice colorful blue coatings. But this is just a side effect which was not interested for us in this application. So if we now look at the properties which we are obtaining, it is quite nicely visible that the better performance we get at those treatments at 400 volts when we are not destroying too much of our particles which we have added. And also that there is a light or the nice trend that with increasing amount of particles, we also get more or higher degradation rate of methylene blue, which was actually our model organic dye in the solution, which should be degraded. And you see that with the same processing and the same amount of particles, when you go on the 500 volts, you have much less degradation rate compared to the 400. So basically all depends on how much of the titanium dioxide we are able to immobilize on the surface and which is then available for the degradation of the particle. So let me show you now the second example, how we can actually functionalize the coatings. And this is for aluminium. Now we have the chance actually to work also with acidic electrolytes, which we did here. The pH was somewhere around 3. And this is an explanation why we cannot use the same approach for the magnesium, because magnesium PO process, we cannot start with this pH value. And this electrolyte, what we have used here, the potassium titanium oxide oxalate dihydrate, simple electrolyte, is not working for magnesium, but relatively nicely, as you can see also on the picture, which is taken from the process for the aluminium substrate. And here we have something new. Actually, somehow it was even a surprise for us, because with this electrolyte, we have deposition of titanium dioxide, which comes obviously from a decomposition of the oxalate, titanium oxide oxalate complex. And that gives us the chance to actually get pure titanium dioxide layers on aluminium, where we normally would expect when we do standard electrolytes, a treatment will give us aluminium oxide as the main phase. But here it is different. And that I would like to show you in the coating microstructure, which you see here. On the left, you see the SEM picture. The top layer is the titanium dioxide. Then comes an interface layer, which is a mixed oxide between aluminium oxide and the titanium dioxide. And you see this clearly also nicely in the mapping, that there is a layer that is rich in oxygen, the high yellow one. And in between, we have then the titanium dioxide layer on top and this interface layer that contains aluminium. And we have also done line scans in different and following different depths of these things, the phases coming from the surface of the coating going down to the substrate. And we were looking at the anatase and the rutile peak. And this you see in this part, about 80 micrometer in depth. We were following the distribution of those two peaks. And you can also see here in the diffraction patterns here that there's an interface layer coming that is related to aluminium to titanium oxide 5 phase, the mixed oxide. So the main point here is actually that we are not sure what phases we have in this. And we did effective diffraction patterns, and we were checking what happens when we are increasing the treatment time. And the ratio between anatase and rutile is relatively balanced for shorter treatment times. But if we extend the treatment time, and here it was a constant current treatment, which means basically that we have with increasing treatment time more energy input, the ratio is changing and rutile becomes to demonstrate. And somehow when we are looking here, in that case, it was the degradation of methyl orange, which we were studying, that it is not a clear indication actually that with the longer treatment time or whatever, we get better properties for the catalytic activity on the surface. The optimum what we found was for 10 minutes actually. And this information we took and we wanted to optimize it. and this is the second part of the aluminium presentation, is dealing with how we can now get a better ratio between the anatase and the rutile. And for that, we have actually added again, similar to the magnesium example. In the beginning, we have added from 5 up to 30 gram per liter anatase particles to the electrolyte. 30 gram was somehow the upper limit. More we could not add because then we had problems with the stability of the discharges in the electrolyte. So again, the same mechanism, but now we have added also the particles. But you see on the cross sections, which we are shown here for the different amount of particles added, definitely the surface or the microstructure is not really changing. We still have this structure that we have titanium dioxide on the surface, and then comes this mixed oxide interface layer. And we have checked, we have relatively stable titanium concentration at the surface, which is not a surprise because it's titanium dioxide. Rather in rutile nor in anatase, we don't know it is. For that purpose, we have done again the X-ray diffraction. And if you look on the diffraction diagrams, you see clearly that the ratio anatase becomes more and more when we're adding anatase as particles to the electrolyte, so we can tune the ratio. And if we are looking here on the photoactivity on the surface, we see that for the 30 grams, actually we reach better performance. Surprisingly, and we still don't know why, if we do not add any anatase, the 10-minute treatment, which we have performed, is the second best in having the second best in the performance of photocatalytic activity. But we see also that there's a clear trend that actually from the beginning, when we have 5 grams to 10, 15, the activity is increasing, but for some reason we have without without anatase addition, still reasonably good properties for our coating. So the conference is about corrosion and degradation. So I would at least at the end also talk a little bit about the degradation of those coatings. So from the application point of view, we should have stable layers in quite aggressive solutions. So we were testing here for 2 weeks how the performance is in 3.5% sodium chloride solution. And you see that most of the coatings does actually not show any corrosion marks. We see on some, for example, when we have no anatase added, a little bit black and also some white. I don't know why it is black in the condition when we have no anatase added and white, but mainly those spots are actually aluminum oxide, which are sealing some of the open porosity. And what we definitely do not observe is actually a dissolution of the coating. The coating itself is stable, but the substrate underneath can react. But the good thing is that it contributes to sealing of the coating, and the degradation somehow stops in those locations where it happens. If there is no coating, that's shown on the right side, we basically have we have relatively strong corrosion on a simply aluminum not coated sheet. And what else is a typical mechanisms for PO coatings is somehow flaking off. That happens when there is too much corrosion in the interface between the coating and the substrate. Then corrosion products like the hydroxide has a much higher volume, and it basically can cause stresses. And if the stresses are too high, the coatings can basically flake off. This we see only somehow in the regions where we had the electrical contact of the, where we have no coating and we had the electrical contact for the PO processing. In that regions, we see a little bit and very few traces of flaking off as one of the additional corrosion mechanisms, but the major surface is free of this quite destructive corrosion mechanism of PO coatings. So let me come finally to the end. I was reaching my time. So the PO coatings on light metals do have basically inherent multifunctionality, because when we are producing ceramic type of coatings, we are always increasing wear and corrosion resistance. But with this presentation, I hope that I could show you that it is possible to add even other more interesting functionalities and maintain wear and corrosion resistance in principle, so that we have really multifunctional coatings. And we can do this by using particles. Particles in principle are nice because it is basically offering you a large flexibility. You can transfer particle properties to the coating, and it doesn't matter whether it is photoactivity, whether it is magnetic properties, or whatever you want. It is, if you are able to incorporate enough of the particles, you will change the coating properties towards what you want with the particles. But however, particles in PO processing are more demanding from the PO side. And from that point of view, yeah, one has always to think. And to having an alternative, for example, functionalize the coating directly from a simple electrolyte is somehow from industrial point of view much more promising. But however, you see, you have less varieties when you try to do this. You are more restrictive in the selection of substrate, in the selection of electrolytes, but you have a much simpler PO processing. And finally, yeah, photoactive surfaces can be generated on magnesium and aluminum alloys using the PO process. So thank you very much for your attention.
Thank you, Carsten, for this very interesting talk about functional PO coatings. I'm looking to questions and answers. If there are any questions and answers at the moment? Right now, I don't see any answers related with this talk. So then probably, question and answers you can ask. I don't see any. Then I think we can go ahead with our next talk, and then Carsten Blawert will be glad to answer your questions, which will appear in questions and answers. You have a chance to post your questions to question and answer window, and then it will be taken and answered later. So thank you very much, Carsten, for this presentation. And we continue then with our next talk. So our next talk will be given by Dr. Mohammad Uddin, and he is coming from University of South Australia, and he's going to talk today about also a different type of application of protective coatings and also functional coatings for biomedical applications. So he is going to talk about hybrid surface modification for biodegradable magnesium alloy implants. And Dr. Uddin, please, floor is yours. You can start your talk.
Okay. All right. Okay. So no, thanks for your introduction and also the inviting me for this conference to present our work here. I think after listening to a presentation by Dr. Carsten, so he has been talking about quite innovative kind of a PO coating by injecting kind of a particles into the coating, which is quite interesting for me to learn today. However, so I'd like to present kind of a my title saying that is the hybrid surface modification approach, basically to enhance the surface integrity and corrosion resistance of the biodegradable magnesium alloy. So we are taking the kind of AZ31B as a sample. So this work is performed with my other colleague and my student as well. So Professor Colin Hall, he's my colleague in Future Industry Institute in University of South Australia, and Vincent Santos is one of my PhD students working on this project as well. So I think the background of this topic is, as you know, the magnesium alloy is a biocompatible material, and so why we need to actually consider this material as an implant. So because the properties of the magnesium alloy is very close to the human bone, and also the magnesium can be absorbed by the human body over the time. So because of this kind of superior properties with the magnesium alloy, so magnesium alloy is being considered as potential candidate for fixation, as an implant for fixation of the bone fracture, and also other applications like the stenting, and also the tissue engineering as well. So in this topic, basically, we are our main plan is basically how we can actually develop a magnesium-based implant that can be potentially being used in the human body to fix the bone fracture, for instance. So, however, the main concern with the magnesium alloy is its fast corrosion, and especially when it comes in contact with the saline environment. So the first degradation because of the corrosion process itself. As a result, the magnesium actually loses its mechanical integrity even before the bone healing is complete. So, and because of this, of course, the bone implant performance also being deteriorated and basically causing the failure of the implant at the end. So there is maybe potentially need secondary surgery to fix it. So in this talk, basically, the question is how we can actually control or improve the corrosion resistance of the magnesium alloy so that we can take the benefit of the magnesium alloy into the next level so that we can use it into the future clinical applications. I think that there are many techniques I think being used in the current practice in the research, like what other speakers already have discussed in their presentations. So today, so there are the techniques. First technique is developing a kind of a new type of alloys with the magnesium, adding different chemical elements into it to really improve the microstructure and also to improve the corrosion resistance and other mechanical properties. So this is the first one people have been trying, and also but the problem with the new alloying or adding new materials is always there will be potential toxicity, like we need to do a lot of trial and test and a lot of study we have to do to understand, okay, what kind of a new alloy or element could be added. So next one is the coating. So this has been predominantly studied in the literature, and like other speakers already have indicated, like even Carsten earlier mentioned. So trying to use the different types of coating, really biocompatible coating, thin to thick coatings to really improve the corrosion resistance. So coating is generally very thin. It could be porous, and there is a potential of breakage and losing the integrity. But still, there are some coatings is quite successfully developed, and they're providing quite beneficial effect into resisting the corrosions. Third techniques also being studied is mechanical processing. So instead of adding new kind of coating layer onto the substrate, why not we just process the substrate material by kind of a process, which is the mechanical processing, we would say, by doing some plastic deformation or straining into the material microstructure, and so that you still can get some benefits in terms of corrosion resistance and other mechanical properties. So one of the process in this regard is basically you apply some sort of microstructural change by doing a mechanical treatment, which could be machining of the substrate, or could be grinding, it could be short pinning. There are different techniques, ball burnishing or laser pinning. So there are different techniques are being used to really improve the corrosion resistance without using alloying or coating. So, okay, now question is that, okay, what direction we'd go? And so one of the potential ways, so each technique or each approach has some benefits, pros and cons. So, and so what is the potential way we can really improve the corrosion resistance further, and so that we can use the magnesium alloy in future applications? So in this research work, what we have been trying to do, we say, okay, let's say we try to have a kind of a hybrid approach or synergetic approach, combining a mechanical technique and also the coating technique. Okay, so and we found that we think, okay, if we actually take the substrate of the magnesium alloy and if we apply kind of a ball burnishing, okay, which is a mechanical technique, you just by applying a kind of a force, and the ball would be rolling onto the surface, and it's like a cold mechanical working you do on the material. So by doing that, you basically can improve the surface texture and also create a kind of a microstructural change into the material. And by doing that, you can perhaps minimize the kind of a pores or cracks, and also can create some sort of internal stress, compressive residual stress that could potentially prevent from the corrosion. And and then we said, okay, after we do the corrosion, why not we then apply kind of a coating, which could be not only adding another layer of the corrosion barrier, but also it can give you kind of a more benefit in terms of the osteointegration. So the hydroxyapatite is another kind of a compound we can consider here, and we can deposit that hydroxyapatite on top of the mechanically modified or burnished surface. And so so we can actually, hydroxyapatite can provide the two things. One is additional corrosion barrier, and also providing the kind of a helping to bone to grow around the implant. Okay, so in this research we are basically study this kind of combined approach, which is a combination of ball burnishing and the hydroxyapatite. So we are going to do the ball burnishing first, and then we are going to deposit hydroxyapatite on top of there and see how the combination of this hybrid modification or treatment can improve the surface integrity as well as the corrosion resistance. So that is the objective we are just trying to actually investigate in this particular study here. So by looking into experimental setup, so this is the experimental setup we have here. So what we have done, we have taken the magnesium plate of a certain thickness, and then we considered a specific coupon, test coupon. Then we did a kind of a burnishing. So this is our burnishing tool, which is, there is a small ball which is being controlled by the hydraulic pressure, and you apply the force onto the material, magnesium material. So, and you can actually control the force, and also you can control the feed rate, how fast the tool or ball is going to rolling onto the material. You can also change the step. So we have taken the kind of a zigzag burnishing path to modify the surface. And next we have done the hydroxyapatite coating. So we have used kind of a very standard 3 electrode potentiostat to actually deposit the HO coating on top of the modified burnishing sample. This is the sample you can see here. And we have got the hydroxyapatite electrolyte we have in the beaker here. So this is a very standard process we have considered. So some of the parameters involved in the ball burnishing and the HO coating. So ball burnishing we have done with a very hard silicon carbide ceramic ball, 6 millimeter in diameter, and then we have used the like 200 bar of the hydraulic pressure, so which is equivalent to 565 Newton, so which is a fairly reasonable force we apply to make some modification into the microstructure. And so feed rate was 100 millimeter per minute, and 0.2 was the step over, which is side step. And in terms of the HO coating, we have at the beginning we have got a electrolyte, a combination of the HO composition and with the pH 5. And we have done the whole HO coating, which is the electrochemical. We have used the electrochemical deposition process here. at a constant current density of 6 milliamp per centimeter at for 2 hours at 23 degrees centigrade, so at a room temperature pretty much. So after that, after the electro deposition of the HA coating on the sample, then we did that kind of alkaline treatment in like a 0.25 mole sodium hydroxide solutions for 4 hours at 60 degrees centigrade. So this is to actually convert, because the HA is generally is formed as a calcium phosphate based coating. So we have to do kind of and it becomes very porous and amorphous. And so we use the alkaline treatment to convert the biphasic coating, HA coating, into the complete HA coating. So some of the results we have got here. So we have done some ACM microscopy of the surface of the untreated, burnished, and then we have also kind of a HA coating on the untreated surface, and also HA coating on the burnished surface. We can see that the burnished surface is fairly smooth because we modified the surface and removing the lots of peaks and valleys. And then after we deposit the HA coating on the untreated and the burnished, as you can see, we can see fairly very platelet-like crystal structure of the HA coating deposited onto the both surfaces. So, however, we can see that burnished, when you deposit the HA coating on the burnished surface, we can see very smooth, very compact, and kind of a dense HA coating structure being deposited. But we can see a little bit of the damage or delamination in some places of the HA coating when we deposit onto the untreated, I mean, without varnishing. And some of the magnified view of the HA coating, we can see very flower-like crystal structure, and then the plate, those crystals are around size would be 10 to 50 micron of the size, and the thickness would be, as you can see, that is thicker, is around 5 micron of the thickness crystal plates being deposited. So this is our surface topography, and then we have done some surface roughness investigation. We can see that because the HA coating is a bit rough, and because of its plate-like structure, it's not like a very uniform, like a completely dense, like homogeneous. So because of that, we can see that the surface roughness is getting higher in the case of as compared to the untreated or the burnished surface. So it's a bit rough surface. So of course, the HA coating being a rough surface of a coating is sometimes could be beneficial in terms of other osteointegration, and then also the bone growth around the implant. So this is the surface roughness is a bit higher as compared to the untreated and the burnished surface. We did some EDS analysis to see the chemical composition of the treated surface and untreated surface. So we can see that compared to the untreated and the burnished, there is no any coating over there. And we have seen that we can see the presence of the calcium and the phosphate, which is the key element of HA coating. And so that also indicates that the HA coatings are being deposited into the surface successfully. In order to further investigate the chemical more accurately to determine the presence of the chemical composition, elemental composition on the coating, we also have done the XPS, the spectra analysis. So, and XPS analysis gives us a bit more, the confirmation of the presence of the elements. Often the EDS may not give us the actual information. So we can see that also here, the presence of the calcium and the phosphate, and also the magnesium in the case of the untreated surface. So, and also we have plenty of oxygen and some of the aluminum element also here you can see. So which is part of the composition of the magnesium alloy, which is AZ31B. So we can see that here there is a little presence of the magnesium in the case of the untreated and HA coated surface, because the HA coating is covered the substrate. But in the case of the HA coated surface, either untreated or plus HA or burnished plus HA, you can see the calcium. There's a large peak of the calcium, so that also indicates the presence of the calcium. And similar to calcium, we have also the phosphate element presence in our XPS expector. So this is another confirmation of the deposition and successful formation of the HA crystal. And one of the indicator of the HA is also the calcium phosphate ratio. So we quantitatively also analyze what is the calcium phosphate ratio. We found that in the case of the HA coated surface, the calcium phosphate ratio for the burnished plus HA is around 1.62. But in the case of the untreated plus HA, it is a little bit lower than the even 1.62. So what we are saying that when you deposit the HA coating on the burnished surface, we have got a higher concentration. I mean, the ratio is higher, and generally, which is the standard HA crystal stoichiometric ratio for HA is basically 1.67. So we are saying that when you do the HA coating onto the burnished mechanically treated surface, which is burnishing, we can achieve the calcium phosphate coating very close to the close to its stoichiometric ratio. So this is another confirmation of the HA deposition and burnishing with HA coating can achieve. Furthermore, we have done some further XRD analysis to actually investigate the crystal phase, I mean the compound formation of the HA. So we can see that this is the untreated surface where we can see mostly the magnesium. But when you deposit the HA coating on top of the untreated of the burnished surface, we can see the presence of the HA compound. We can see that especially when you have the peak, the diffraction angle around 27 degree to 30 degree, you can see the formation of we can see the HA crystal peaks onto the surface from the XRD. So this is, and we can see that the peaks are a bit more and higher, a little bit higher in the case of the burnished plus HA coating as compared to the untreated plus HA coating. We also looked into the cross-section of the coated surface, and we can see that cross-section of the HA coating by SEM and also the EDS. We can see this is the untreated plus HA coated cross-section. And we can see that in the cross-section, generally, this is the substrate, and then we can see the bit of a formation of the magnesium hydroxide. This is very common when you deposit any kind of HA coating onto the magnesium, because it has initially forms a magnesium hydroxide barrier, very thin barrier layer, and then we have on the top of that we have got a HA coating. And we can see the same thing exactly also in the burnished plus HA coating. So one of the interesting things we can see here, perhaps we can see in the case of the untreated plus HA, we can see the magnesium hydroxide is a bit higher, layer is a little bit thicker than when you do the HA coating on a burnished surface. And we can achieve the kind of a thickness of the coating around 95 micron or up to 100 micron thickness for both cases. So HA coating is being deposited pretty much quite uniformly, as you can see here, and quite densely. And these EDS pictures on the top and bottom actually just confirm again the calcium and the phosphate elemental presence into this cross-section of the coating as well. Because in order to confirm the surface integrity, so how the burnishing also has improved the mechanical property, which is the hardness, we measured the nano hardness by nano indenter onto the burnished surface and also the untreated surface. So because the burnishing is a mechanical cold working process, we expect the kind of a microstructural change and deformation of the grain. We expect to see some sort of hardness improvement. So we can see that burnishing actually caused the improvement of the hardness onto the top surface, which is around right here and at the top surface. And if you go to along the depth, along the cross section, if you go along the depth from the top surface, as you can see the hardness has decreased. So that means we can see that because of the burnishing surface modification, we can improve the mechanical hardness at the top layer up to like around 700 micrometer depth. So hardness actually diminishes as you go down. So this is another benefit of by doing the mechanical surface treatment. So you can improve the mechanical property as well. To see that what happened into the microstructure of this material. So this is the untreated microstructure. We can see that the grain of the microstructure is quite large, as you can see here, quite uniform and quite large grain distribution. However, when we apply the burnishing, we can see there is a bit of kind of a change into the microstructure. We don't see much kind of the grain refinement, but however, you can see kind of the twins into the at the top layer. There's a twin and the twin bands being actually generated into the from the top surface, and as we go down, we can see the bit of more the as bulk distribution of the microstructure. So there is not much change of the grain. So these twins or twin band generation could be because of the burnishing process, and that is actually, we expect that this kind of the change of the microstructure by forming the twins or twin bands is going to increase the surface activation energy onto the top surface of the magnesium alloy, and that's actually are going to activate that's are going to enable to the deposit the HA coating much more effectively onto the surface. So that was the kind of a hypothesis we have been looking into here. So why actually the HA coating was much more better dense in the case of the burnished surface. We also looked into some other mechanical properties, residual stress. We can see that the residual stress, by applying the burnishing, we can also induce a kind of a compressive residual stress into the top surface, and it is actually decreasing as you go down along the cross section. So compressive residual stress is always beneficial in terms of suppressing the cracks, potential cracks, and also the maybe it's going to actually also prevent the potential corrosion as well. So we looked into the residual stress into the feed direction and also the force direction during the burnishing, and we can see that in the both directions the residual stress we have been able to create the compressive residual stress than the tensile stress. So this is the benefit in the literature. It says that the compressive residual stress is going to always improve the corrosion resistance as well. Just to see how the HA coating is actually bonded together with the surface.
So
mechanically,
I think we have to come very soon to the end in order to not create further delay. Yeah, sorry for interruption. Yeah.
Okay, thank you. We can see that the HA burnished plus HA coated, the addition strength is also quite high. I mean, you can see which is 13.2 megapascal, and this strength is pretty close to the generally recommended strength, bonding strength for any coating. And we also have done some sort of contact angles just to indicate the weightability, and we know that the biomaterial and biocoating has having a much more weightability is going to increase the implant osteointegration of the implant. So this is the corrosion results. I like to highlight mainly because this is the main results. So we can see that by applying compared to the untreated surface and by applying the hybrid modification, which is the burnish plus HA coating, we can see the corrosion potential has been shifted to the positive. So corrosion potential has increased, and we can also see that the corrosion current density has been lowered. So as you can see, the shift of this line from the bottom to top. So that means that the higher corrosion potential means it's better in terms of the corrosion resistance. And this is the summary of the corrosion results we have got here. And this is just indicates again that the burnish plus HA coating is giving the highest corrosion resistance compared to the untreated or even the simply burnished surface. As you can see, the corrosion potential is higher, and also the corrosion current is also lower. So that means the higher corrosion resistance, in fact. And we have got some corroded topography, and just to show you that the burnish plus HA coating actually preserve the surface pretty good, and then and also as compared to the burnished surface, which has got a kind of a corroded product, significant corroded products, but in the case of the untreated, it is quite high. So that means having the burnish plus HA coated giving the additional corrosion barrier and protecting the surface here. And finally, I have got a corroded elemental analysis. This is just to show you the retention of the elements as being the surface being degraded. So we can see that in the case of the burnish plus HA coating, HA coated surface, we can see the calcium and phosphate increase, which is quite natural because it has got a HA coating on the top, but we can see the less amount of the magnesium in the case of the Barnish plus HA coating. So that means the less degradation or less corroded products being generated in the case of the hybrid treated surface. So finally, just to conclude, I like to show that the burnishing is going to improve the surface integrity in general, but we can deposit the very dense and the compact flat like HA coating onto the burnished surface, thickness of the 100 micrometer. And burnishing not only increase the HA coating deposition, but also increase the hardness at the top surface. It also induced the microstructural change up to 95 micron deeper level with some twins and the twin bands, which we believe that is going to increase the surface activation energy that allows to deposit the HA coating successfully. And burnishing also induced the compressive residual stress that is beneficial for reducing cracks and also fatigue and helpful for the corrosion protection. And we demonstrate that, okay, overall the burnished and also the burnished plus HA coating is going to actually provide higher corrosion resistance, and hopefully this kind of process is going to provide the additional resistance for the degradation, preventing the degradation of the magnesium alloy. So that's something, that's the end of the presentation, and thank you very much for your time.
Okay, thank you very much for a very interesting presentation about surface functionalization and modification for biodegradable alloys. Unfortunately, we have not really time because we are accumulating delay for too much discussion, but there are 5 questions in questions and answers. Could you please look there and answer that everyone that can see your answers to those questions? I think that would be great if you can do it reasonably soon. And thank you very much once again. Yep. And we move to the next presentation today, which will be given by Rubén del Olmo from Complutense University of Madrid, and he will talk about PO coatings with corrosion inhibitors. So please, the floor is yours.
Well, good morning, everyone. Thank you, Mark, for the introduction. Professor Zheludkevich. My name is Rubén del Olmo, and I'm going to present my research work entitled In situ incorporation of corrosion inhibitors into plasma-electrode oxidation coatings on 2024-3 alloy. Well, this slide shows the structure of the next presentation. I'm going to start talking about introduction in order to explain the motivation of the present work, aims and approach, experimental part, carried out, results and discussion, and finally conclusions of the present work. Well, first of all, I'd like to highlight the most widely used aluminum alloy in the aircraft industry is 2024-3 aluminum alloy. This is due to its high specific strength, which allows decreasing fuel consumption and gas emission during the aircraft life service. However, the main limitation of this alloy is its low corrosion resistance. For this reason, this alloy is usually surface treated with a multi-layered protection scheme, which consists in a pretreatment, a primer layer, and a mono or bilayered paint system, depending on its application. It should be noted that the quality of this multi-layer protection scheme depends on the quality of this pretreatment, which must show high adhesion and corrosion protection. So far, the most widely used surface treatment is chromic acid analyzing, which promotes the formation of uniform coatings with thickness comprised between 2 and 7 microns. It's valid for fatigue critical components, offers fair paint adhesion and excellent corrosion resistance. However, the use of chromium-based compounds have been targeted as toxic and carcinogenic. So for this reason, the European Union required its elimination before 2024. An innovative alternative is plasma-electrode oxidation, PO, which is an electrochemical treatment characterized by the use of high voltages, long treatment times, and give rise to the formation of ceramic coating with thickness comprised between 5 and 200 micrometers. And this is useful for wear-sensitive application, conventionally useful for wear-sensitive application in aircraft industry. However, for chromic acid analyzing replacement, this high thickness value is critical for fatigue-sensitive components, and the inherent condition of this process involves high energy consumption. So a possible way to overcome this limitation is the formation of flash PO process, which consists in the formation of PO coatings with low thickness value using low treatment times. And a possible way to increase its corrosion resistance is the incorporation of corrosion inhibitors into the coating structure. So the main goal of the present work is growth of flash PO coatings on 2024 T3 aluminum alloys with the incorporation of several corrosion inhibitors. Then perform a screening process based on surface appearance, thickness, and corrosion resistance. And finally, the evaluation of selected coatings according to characterization techniques, corrosion behavior, and paint adhesion. Our base material, well, regarding the spindle part, our base material is 2024 T3 aluminum alloy. We perform the specimen preparation according to industrial procedure prescribed by Henkel company. Study the formation of flash PO coatings using several types of electrolytes and different corrosion inhibitors, and perform study these coatings by characterization techniques like scanning electron microscopy, X-ray diffraction, and water coated angle. The corrosion evaluation was performed by electrochemical impedance spectroscopy and neutral spray test according to this aircraft standard. And paint adhesion capacity was performed according to this standard and with paints provided by AkzoNobel. Well, in this moment so far, we know that PO is a high-cost treatment. PO coatings are usually thick, and corrosion inhibitors is an effective way to increase the corrosion performance. So we would like to know if it's possible to develop thin and cost-effective PO coatings on 2024 aluminum alloy, and how corrosion inhibitors affect the morphology, corrosion behavior, and paint adhesion of these flash PO coatings. So for this, our first stage was performed a screening process using low current densities, a voltage limitation, and short treatment times in different electrolytes. After the first screening process, based on the electrochemical measurements, we conclude that phosphate electrolyte is the most suitable to study inhibitor loading processes. We studied baratate, molybdate, lanthanum, tin, tungstate, and thorium. And according to the impedance modulus during 1 hour of immersion time in sodium chloride solution, we conclude that thorium containing and tungstate containing flash PO coatings was the most corrosion resistant coating. So for this reason, these coatings were selected for further analysis. Well, the both-stain curves of these coatings reveal similar trends in all cases. For inhibitor-free PO coating, the black one, and the red and blue one was for inhibitor-containing coatings, thorium and tungstate, which reveals lower voltage values and lower breakdown voltage values also. The energy consumption of these coatings was significantly lower than in comparison to conventional PO process. And it's true that in comparison to conventional analyzing, we are in the slightly higher values. But as a counterbalance, we use lower treatment times, we use eco-friendly and low-cost electrolyte, and we perform the formation of these coatings at room temperature. Regarding the micrographs obtained by scanning electronic microscopy, we obtain a similar porous-like morphology, which is typical for this type of coatings, and we obtain a thickness value for inhibitor-free PO coatings in comparison to inhibitor-containing PO coatings. We also confirm the incorporation of thorium and tungstate species in the coating structure. In the case of thorium, is incorporated in the outer coating part, while in the case of tungstate was incorporated uniform in the coating structure. And the X-ray diffraction patterns reveal the formation of gamma alumina as the most predominant phase, probably due to the consequence of the low voltage used in the present work. And no thorium and tungstate species were detected in these X-ray diffraction patterns, and probably it's due to its low concentration in the electrolyte. Regarding the corrosion behavior, in short term corrosion behavior, we achieve a high corrosion resistance for inhibitor-containing PO coatings in comparison to inhibitor-free. And this could be related to less soluble thorium and tungstate species in the coating structure. Although in the case of long-term corrosion study, we achieve similar corrosion protection. Regarding water-coated angle value of this coating, we confirm that all coatings were hydrophilic. And in the case of inhibitor-free PO coating, we achieve a very bad paint adhesion. By contrast, for inhibitor-containing PO coatings, we achieve an improved paint adhesion, especially optimal in the case of thorium-containing flash PO coating. Then we evaluate this corrosion behavior as a full system with paint parts by neutral spray test when in 1,000 hours. These both inhibitor-containing PO coatings, and we obtain similar long-term corrosion behavior in both cases. And also we didn't detect any blisters of pitings, formation of pits during the test. So in conclusion, we can conclude that it's possible to develop thin and cost-effective PO coatings with thickness compressed between 4 and 6 microns and low energy consumption on 2024 T3 aluminum alloy. Also, regarding the incorporation of corrosion inhibitors, we ascertained that therine-containing flash PO coating reveals the best results in terms of both paint adhesion and corrosion behavior after neutral sand spray test. Finally, I would like to thank my research group from Universidad Complutense de Madrid, preparation and derivation of materials, and also Dr. Peter Visser from AkzoNobel. Also, I would like to thank all people involved in the different companies and universities in the Magic Clean Sky project. Finally, Aldis Manoles, thank you everyone for your attention.
Thank you very much for your presentation. I don't see at the moment questions. I have one question from my side. When you are adding corrosion inhibitors into the PO layer, do you think any kind of corrosion inhibitors can work, or there might be also a negative effect of inhibitor on the PO structure, because that's something what we have experienced in the case of magnesium substrates? Did you observe such negative effect of inhibitor on the aluminum-based substrates?
And no, I also report corrosion improvement, practically in all cases. But for example, in the case of anionic inhibitors, vanadate, for example, or molybdate, we achieve bad corrosion performance. And also I studied the combination with EDTA, and as a kind of effect, we only observe as expected corrosion performance when it's combined with cationic inhibitors. But in the case of molybdate and vanadate, I obtain a bad corrosion performance in comparison to PK phosphate-based electrolyte. This could be related to the formation of unstable oxides during this formation, the lower coating stability, according to my literature review, for sure. Because we only detect a corrosion improvement with this tungsten deuterium containing PO coating. So for this reason, we decide to select these coatings for further analysis. We discussed it a little bit in the paper, but only in these cases with the bad corrosion performance.
Okay, thank you very much then. And since there are no further questions, we can go ahead with the next talk. But again, if you see some questions and answers related to your talk, please check and then answer in Q&A. Yep. Thank you very much.
Thank you very much.
Now we are moving to our next talk, to be given by Peter Rodič from Jožef Stefan Institute from Slovenia, and he's going to talk today also about protection of 2024 alloy, but using a different approach with hybrid sol gel coatings, although functionalized hybrid sol gel coatings. Please, Peter, floor is yours.
Okay, thank you very much. Hello to everyone. My name is Peter, and today I will present one of the ideas how we can protect the aluminium alloy with coating. So that means that despite the aluminium alloy contains a lot of intermetallics randomly spread in the aluminium alloy with different shapes and different potentials, our idea is that we will apply, for example, only 3 micrometers thick hybrid sol gel coating on the surface, which will protect the aluminium surface against aggressive corrosion media, for example, chlorines media. So, of course, there are many alternatives, but today I will focus on hybrid sol gel coatings. Why is the reason? Because this approach has many advantages, and one of them is definitely that we can combine both inorganic and organic compound in one material. That means that we can tailor, we can choose different composition, and that means that we can get the material with different thermal stability, hardness, durability, and so on. Moreover, these hybrid sol gel coatings can be also modified with acrylate-based systems. That means that this kind of molecules can be easily copolymerized in our hybrid sol gel network. So here is the experimental part. So as I mentioned at the beginning, we have aluminium alloy 2024. So here is the composition. And prior deposition of coating, the surface was water grouted with silicon carbon emery paper to obtain the smooth surface. And this was prepared for coating deposition. All coatings were synthesized in this closed reactor because we tried to prepare the best conditions to get the conditions which can be repeatable after a certain time. And also the reason is that we want to follow the reactions every minute with FTR system. So after the preparation, we deposit these coatings with a deep coater, and we apply one layer of these coatings on the previously ground surface. After that, the coatings were cured at 180 degrees for 1 hour. After that, of course, we also perform some characterization, topography, and so on. So we also measure the thermogravimetrical analysis and do some analysis with focused ion beam scanning electron microscopy, and also we perform some electrochemical impedance, which were performed in 0.5 sodium chloride. So here is the synthesis. So the flow chart of this this solution preparation consists of 2 sols. First sols contains this silane organically modified silane precursor, which is combined with methyl methacrylate together, and in the presence of initiator polymerized together to get the final solution. For this presentation, we also replaced 20% of this methyl methacrylate with perfluorooctyl methacrylate. The reason is that we want to figure out what is the effect of this perfluoro group in the synthesis of this sol gel coating. However, this is the sol 1. So here we will mainly focus on copolymerization. In the second part, this is the inorganic part, where we add the water as a reagent to perform the hydrolysis and condensation reactions. And after combining both sols together, we will obtain the siloxane network. However, all the parameters are also described in these references. You can find it more in details, what are the other parameters such as polymerization time and other conditions. So let's take a look some results of this sol gel preparation. So here is the real-time FTR spectra of initial methyl methacrylate and organically modified silicate. When we combine together, we will see that the characteristic bands for methoxy groups are still present in the spectra. But on the other hand, we can see some differences about the bands related to double bonds. And if we take a look more closely, we can see that the intensity of double bond decrease with copolymerization time. So that means if we wait for example 4 hours, the band intensity decrease. The reason is that acrylates group reacts together and form a network in our first solution. But if we take a look more closely, we can see that this process is quite linear. So we figure out if we compare the band area, we can see that this band area decreases slowly with copolymerization time. On the other hand, if we replace part of this methyl methacrylate with perfluoro group, we can see that the slope of this reaction is different. So that means that these acrylates in our solution has some effect on further reaction. But what kind of effect? Here is just present the reaction before addition, before combining both sols together. So the inorganic phase. So the reaction of inorganic phase, which was hydrolyzed in the presence of water, we can see that this reaction this water react with epoxy group, and new bands which are characteristic for copolymerization are present in our spectra. That means that when we add this solution to previously copolymerized solution, this silanols group can react with our copolymerized species, and we can obtain the final Sol-Gil solution. So this is very important to understand the reaction, and further when we will compare the characteristic of this coating, we have to know that the addition of acrylates in our solution is very important. Here are the thermogravimetrical analysis. So if you take a look at plot of this thermogravimetric analysis, we can see three different areas. The first one, of course, corresponds to water and solvents evaporation, but the most important is the second one, which is related to condensation reaction between all species which are present in our solution. And of course, the third is, of course, the thermal decomposition. However, if we compare the coating without and coating with perfluoroacrylates, we can see that coating with perfluoroacrylates is more stable. So that means it has, when we add these molecules in our solution, we change thermal stability. Moreover, if we also characterize the height pressure difference scanning calorimetry, we can see that this peak, which is characteristic for condensation, is also shifted to higher temperatures. Here are the top view sim images of these coatings after deposition on aluminum alloy. So we can see that these coatings are crack-free coatings. They are very smooth and without any cracks. So that means that these coatings covers the aluminum alloy surface evenly. This is very good. But at the other hand, we can see very small, these nano-sized silicon-based domains which are present, randomly present in our coating. Moreover, we can see these domains also if we take a look the cross section of this coating. We can see that these silicon domains are present also inside of this coating. However, if we take a look the thickness of this coating deposited on aluminum alloy, it is around 2.8 micrometers. On the other hand, coating with fluorinated acrylates, we can see that these domains are a little, they're larger, and also they are more, they're much more present in the coating. The same also, if we take a look the cross section of this coating, we can see the larger size of these nanoparticles, these silicon domains, and also the thickness of the coatings increase slightly if the coatings contains these perfluoro molecules. However, from this, we can conclude that the copolymerization is very important, has a very important effect on final coating structure and also composition. And here, finally, the electrochemical impedance results. So the aluminum alloy without coating has, of course, very low impedance values. But after coating with this hybrid sol-gel coating, we can see the impedance value increase for a few orders of magnitude to much higher values. That means that this kind of coating present very good corrosion resistance. But on the other hand, if the coating contains also perfluoro molecules, these values are even higher, and it remains even much more stable during, for example, 4 months immersion in sodium chloride solution. So that means that by modifying this coating, we can also tailor and get better corrosion resistance if this coating is if this alloy is coated with this kind of coating. So to sum up, so we try to modify this hybrid sol-gel coating with fluorinated methyl methacrylates, and we figure out that there is very important parameter, and this is a copolymerization process. because this copolymerization process affects on different ways. First is, of course, the size of this randomly spread nano-sized silicon, but also the presence of these molecules change the thermal stability of this coating. However, the most important thing is that this kind of coating presents very high corrosion resistance. And of course, it presents a good idea for further studies of barrier coatings. And maybe this will be presented on next talk. At the end, I would like to acknowledge for financial support and to my colleagues and other centers where we work these experiments. And of course, thank you for your attention.
Thank you very much for the talk, demonstrating excellent barrier properties of this new hybrid solid gel coating for 2024 alloy. I'm just looking if there are any questions and answers. Please, those of you who have questions, you can post it now, or for panelists, answer in live. I'm just looking if there are any hands. Okay, there is a question coming in question and answers. Are these coatings absorbed via chemisorption or physisorption? I believe the question is about the bond formed between aluminum alloy and the hybrid coating.
What is the nature of chemical absorbent? Because the steel and ores groups react with ground aluminum surface, and there is a direct connection with aluminum substrate and coating. So we have quite good adhesion.
Okay, good. So any other questions? I'm looking, I think not. Then I would like to thank you again. And once again, I repeat, if there are any further questions, please check questions and answers. Yep.
Okay,
Thank you very much for this inspiring talk. And we move to the last talk of our session today. I just would like also to remind you that tomorrow there will be second part. Tomorrow or the day after. I mean, in the program, we have also second part of corrosion protective coatings, barrier coatings. Please also don't forget, and I would like to welcome you also to that session. But in this session today, we have a last talk, which will be given by Tamara-Rita Ovari from
Yes, I'm here.
Babeș-Bolyai University from Romania, and she's going to talk a bit about also composite coating, but modified by graphene oxide. As you know very well, graphene oxide being quite hot topic in many areas, including corrosion protection coatings, and it will be very interesting to look into the results of this presentation. Please, the floor is yours. Yeah, you can go ahead.
Hello, my name is Ovari Tamara-Rita, and I am a PhD student at the Babeș-Bolyai University from Cluj-Napoca. The title of my presentation is Surface Modified Graphene Oxides and Silica Composite Coatings and their enhanced protective properties on zinc substrates. So in the introduction part, I will talk about silica coatings and graphene oxide nanofillers, representing their advantages and disadvantages. Silica coatings are widely used on metals to mitigate corrosion because of their extraordinary tolerance to high temperatures, sunlight, and physical degradation. It has advantages such as transparency, good chemical resistance, high flexibility, and good impact resistance. And we know that the siloxane groups of silane molecules form strong covalent bonds with the substrate, generating excellent adhesion among the zinc surface and the silica coating. But despite the fact that silane films are quite hydrophobic, they fall short in offering long-term protection because of their tendency to form cracks, microforms, and low cross-linked areas. Graphene oxide is thought to improve the corrosion resistance of polymeric coatings by lengthening the electrolyte pathway and decreasing the porosity of the coatings, which is illustrated here. This is due to their well-defined structure, high surface area, and small particle size. Major difficulties occur with the dispersion of the graphene oxide nanosheets in polymer matrices, having the tendency to form agglomerates due to their large surface area and surface energy, provides obstacles in achieving great results. So our objectives are to increase the long-term protection of silica coatings and to incorporate the graphene oxide into the silica matrix. Some steps in order to do this are the study of the geo nanofillers and their surface modification, the morphostructural and physical-chemical characterization of graphenes, the electrochemical characterization of the coatings by using impedance spectroscopy, and at least the study of the soil aging. Experimental conditions, well, I don't particularly want to go into details. Important is that we use the 3-electrode system with sodium sulfate electrolyte in order to investigate the coated and uncoated zinc substrates electrochemically. Before that, we studied the GEO and RGO by Raman spectroscopy. We modified the GEO and investigated the graphenes by TEM and SPHERE. About the preparation of the coatings, we used the deep coating method. We had 5 precursor sols, the silica sol, and the other 4 containing the graphenes. After deep coating, a drying process was necessary. On this slide, we can see the Raman spectra obtained for GEO and RGO and the table with the parameter values. We can see 2 major features in the spectra. The G band is associated with sp2 bonding of carbon atoms, and the D band, the D band, which represents the defect or disorder state of the GEO and RGO. The LA value from the equation tells us about the oxidation state of the graphenes. The LA value for the GEO was 17 nanometer, and for the RGO was 35 nanometer, which proves that the GEO has a higher oxidation state and a lower electrical conductivity. So we work with 4 different graphenes, which will be presented in this slide. The graphene oxide, the reduced graphene oxide, then the Aptose modified graphene oxide. Here we can see that the Aptose molecule forms covalent bonds through the ethoxysilane groups with the hydroxyl of the GEO releasing ethanol. It is also possible that the amine of the Aptose reacts with the epoxy groups found on the surface of GEO. And the last one, the PAMAM dendrimer forms covalent bonds through the amino groups with the carboxyl groups of GEO. Here we can see the PAMAM modified graphene oxide. It is important that through chemical functionalization, we can also prevent the agglomeration of the graphenes. In order to prove the modification of GEO, SPHERE spectra of GEO, RGO, Aptose GEO, and PAMAM GEO were examined. We can observe the signals representative for the oxidation groups found on the surface of GEO, which are hydroxyl, carboxyl, and epoxide groups. And in the case of reduced graphene oxide, these signals are not so intense. New bands become visible after interaction of GEO with Aptose around 1000 centimeter on -1. This signal appears, the silicon oxygen carbon here. And the silicon oxygen silicon absorption peak shows the reaction between the Aptose molecules. Nevertheless, the vibration of hydroxy groups disappear in Aptose GEO samples, which corroborates the fact that the ethoxysilane groups of the Aptose react with the hydroxyl of the GEO. In case of PAMAM modified GEO, a new band emerges at around 1650 centimeters on -1, which can be attributed to the bending vibrations of the amide groups here. Furthermore, the characteristic absorption peak for carboxyl groups has been vanished in the spectrum of PAMAM-GO, confirming that the reaction takes place between the amino groups of the dendrimer and the carboxyl groups of the GO. Next slide. The TEM images reveal the characteristic morphology of the graphenes and confirm that the successful functionalization of GO with APTES and PAMAM. Besides, it can be observed that in case of modified graphenes, especially the APTES GO, the thin film of the graphene is torn apart, forming threads. This means that we successfully stop the agglomeration of the particles. The PAMAM-GO seems to have some black spots on the surface that is attributed to the PAMAM molecules. Electrochemical impedance measurements. Impedance data were modeled using the electrical circuit presented in this picture. Table 2 contains the corresponding parameters obtained from fitting the equivalent electrical circuit model to the experimental diagrams. This model consists of a resistor as a solution resistance, a resistor and a capacitor in parallel, which represents the electrolyte resistance through the coating and its related capacitance, and a parallel combination here of the charge transfer resistance and the constant phase element of double layer capacitance. It was a surprise for us that without soil aging, the silica containing RGO sample had the best result. Here we can see on the nitrate diagrams. To be honest, we couldn't find a great explanation for this. The rest of the coatings have similar polarization values, polarization resistance values. Here we can see. On this slide, we can see the details. So just a second. So yes, after 4 weeks here of soil aging, these changes, the silica containing RGO drops at the value of pure silica coating here, and the GO, APTES GO, and the PAMAM-GO offers better anti-corrosive protection. Silica PAMAM-GO having far the best polarization resistance values. And on this slide, we can see the detailed soil aging effect in case of the silica PAMAM-GO samples. On the second week, the coating's RP value almost doubled here, almost doubled compared to the sample coated from the initial precursor soil. After 4 weeks, the polarization resistance reaches 2,488 kiloohms from the 449 kiloohm start value. In the body diagram, we can observe that with soil aging, the silica containing PAMAM-GO coating becomes capacitive, which we know from the fact that this part almost becomes a straight line. And at least the conclusion, so the surface modification of GO improves the corrosion resistance of silica coatings. The soil aging has a major contribution to the electrochemical behavior of the coatings by increasing the polarization resistance of the coatings containing GO and modified GO. And PAMAM-GO introduced in silica presents the best protective properties for zinc substrates. And thanks for your attention.
Thank you very much for your talk, interesting talk. And now we have time for questions. There is a question. So does PAMAM-GO takes time to absorb? Right, shows me. Yeah, that might be the reason for better corrosion resistance with increasing time. So the main idea, if it is this improvement of resistance with time, is related with the absorption process of PAMAM-GO coating. What do you think?
Sorry, I really didn't understand the first part, so I was trying to be attentive to the second part.
I mean, the question from one of the attendees is that this improvement of the corrosion resistance with time, aging time of the system, might be related with the adsorption process of components of the coating, or it is related with something different. Why this improvement is observed?
I believe that if in time more bonds will form, and that's why we will have a more compact coating.
So it's basically it's a curing process, yeah, which is responsible for improvement rather than the adsorption from your point of view.
And the PAMA modified GO and the APTUS modified GO will have this process of curing.
Okay, then thank you very much again, and I would like to thank all the speakers of this session today. Now we have time for lunch break, lunch in Europe, not lunch, definitely in Asia and in Americas. So, but I hope to see you in 50 minutes in the next session of the conference, and I wish you a nice break, and thank you very much for attending this session. Thank you.